let me announce our new speaker. It is Anil Zenginoglu from the Maryland, United States of America. Now we can ready to listen his presentation entitled by Hyperboloidal Compactification for Wave Propagation. Before giving the microphone to the Professor Anil, I want to give my all thanks to him because we are very glad to listen him here, and he was able to arrange his schedule because there is some difficulties in the American local time. Again, I want to say thank you him. So, can you hear me?
Yes, I can. Can you hear me?
Yes, we can also hear you.
All
so
right.
If you are ready, we are ready also listening to you.
Okay, thank you. Yes, it's 4 a.m. here. I just woke up. Thank you very much for having me. Actually, this is the first time. I'm from Turkey. I grew up in Istanbul. I'm a research scientist at the University of Maryland. This is the first time I'm giving a scientific talk in Turkey. Thanks, COVID, I guess.
Thank you so much. Sorry for interruption. Can you make a full screen your presentation?
I think it should be full screen. No?
No. Can you try Control L or try the tools?
So now it's not full screen?
No, you can see the Adobe
yes,
export.
Now, and then now it should be.
Yes. Yes.
You see it full screen?
No, unfortunately.
Interesting.
Maybe
then
you are sharing your screen only PDF because of this.
Let me see why that happens. Let me then use a different program instead of this one.
Okay, you can try.
Work. So not allow me to share at this point. Let's try it again. So, do you see full screen now?
Yes, now we are perfect for the syncing.
Great. I'm just going to try to use the spotlight. I hope the spotlight is working.
Yes, it's working.
Okay, great.
Yes, please.
Okay, so the talk is titled Hyperboloidal Compactification for Wave Propagation. As this is a meeting about the studies on scientific developments in geometry, algebra, and applied mathematics, I thought I structure the talk based on these topics. So here's the talk outline. I will first describe the problem. The specific problem I'm solving is related to the wave propagation. It comes from applied mathematics, but the solution comes from geometry. So it's a geometric construction that comes from relativity. My background is numerical relativity. And then that geometric construction applied to the wave propagation problem solves what we call the outer boundary problem. And this is the structure of the talk. So the problem is numerically computing waves. My background is relativity. Again, we calculate gravitational waves from black holes, but waves are everywhere. Sight is essentially waves. Hearing is acoustic waves. In this case, I'm giving two examples. One of them is the Maxwell equations, where you solve for electromagnetic waves scattered from the surface of an airplane to see the radar cross-section, how the airplane is visible in the radar. Another example is earthquakes, the waves that propagate on the Earth. This is from a 94 earthquake near Los Angeles, Northridge earthquake. And here actually you can see really what you do when you calculate these things numerically. You put them into a box. So these are the box boundaries. And the challenge then is, what do you do at the box boundaries? Because these waves propagate, and wave equation problems usually are posed on unbounded domains, on an infinite domain. But then when you numerically calculate them, you put them in a box, and at the box boundary, you have to make sure that the propagating waves are not hindered by these artificial boundaries, because they are not part of the physical problem. This brings us to the outer boundary problem. We want that the truncated solution approximates the original solution without the artificial boundary. Now, this implies that your boundary conditions must be well posed so that you have a well posed initial boundary value problem. The data that you provide must be transparent to the interior solution. So when the wave is propagating and hitting the boundary, the data must be such that it makes the boundary invisible or transparent. And then the numerical implementation has to be stable, accurate, and efficient. Each of them is actually a difficult and challenging problem, and there has been multiple papers written on this. And they all arise from the fact that you somehow truncate the original solution domain by some artificial outer boundary. This is particularly challenging for wave equations, meaning hyperbolic partial differential equations, because the solutions are oscillating. So if you wanted to calculate the solution on the infinite domain, well, there are infinitely many oscillations on that infinite domain. So that's very challenging. The other problem is they decay very slowly. So the propagation of radiation towards infinity in 3 dimensions is 1/r. The famous fall off of radiative fields is 1/r, and that's very slow. You cannot just truncate the domain, say it vanishes here, and then you'll be fine. That's not the case. So you really have to be careful what you do at those boundaries. This has been an important problem for many decades. There are some famous works by Enquist and Majda in 1977. It's very old. One of the most popular ones is Berenger's perfectly matched layers. But anyway, any of these solutions are sort of, they work quite well, but it's still an open problem because none of the solutions are local and exact. All of them are either approximate or they are global, but not exact. And here comes the solution. And the solution comes from geometry, and in particular, the geometry of space-time. You see, what you do when you compactify, you only compactify in the spatial directions. So when you map infinity to a finite domain, compactification, typically in applied mathematics, people just do it along space. But that's actually inappropriate. It's better, and I will argue in this talk that it's better, to do it along the null direction or along the hyperboloidal direction. So what do I mean by hyperboloidal? So I'm going to just take a hyperboloid. So this is the equation that defines an hyperboloid. You can see it as x squared minus y squared, some constant value. Here I'm using T and R for the TR plane, the space and time. So T is the time direction, R is the space direction, and this is a hyperbola. And as you can see, this is the unit hyperbola, and it acts as a pseudosphere of the Minkowski metric. This is the set of the points that have unit distance to the origin in terms of the Minkowski distance. So unit space-time distance to the origin. In that sense, the hyperboloid is actually a very fundamental object, and it's been known to Minkowski, in his 1908 talk. He has the hyperbola as the kinematic space of special relativity. It's a very fundamental object, similar to a sphere, which is at unit distance, unit Euclidean distance from an origin. Here we have a unit Minkowski distance from an origin. So it's a pseudosphere of the Minkowski metric. And it asymptotes to the null cone. So this T minus R equals 0, that's these blue dashed lines represent the surface, the light cone surface, the outgoing propagating light cone surface. When you send a wave from the origin, pulse, let's say an earthquake, and that's the epicenter of the earthquake, the propagation goes along the characteristics. In this case, the characteristics describe the null cone, and that's T equals R. And this hyperboloid asymptotically approaches those propagating waves. Whereas when you do T equals constant foliations, they actually move away from the propagating wave. They go to the wrong direction. And that's the problem. So when you have the hyperboloid, you can write the spatial metric on the hyperboloids. Here, this is a 2-dimensional plot. Of course, you have to imagine it as a 3-dimensional space. And the spatial metric of this is the unit hyperbolic metric. And the difference, again, the similarity to the sphere and the naturalness of the construction is very visible here. With the sphere, you have a sine function, trigonometric functions. With the hyperboloid, you have a hyperbolic sine function. So that's the main difference. But it has a big impact on the geometry and a big impact on your numerical code when you do this along the hyperboloids. So what you then do is you take one of these hyperboloids, this one, and then you shift it in t, so you shift it along the time direction by some value. So let's say it's tau. These are the shifted hyperboloids, and these provide a foliation of space-time. Just like before, we were using t. Instead of t, now we're using tau. So instead of the standard, what we call them Cauchy surfaces that go to infinity only in the space-like direction, this is going infinity towards the null direction, and that's called null infinity. So you shift them by tau, you define the tau as your new coordinate, and then you write your metric, the Minkowski metric, in terms of this new coordinate, which makes your spatial slices exactly the slices of the hyperboloid. So it's hyperbolic geometry on your spatial slices. And now once you have hyperbolic geometry, you can compactify. So now we map the infinite domain in Xi or the infinite domain in R, where R goes from 0 to infinity, to a rho where rho goes from 0 to 1. And then you get the Poincaré disk. Some of you will recognize this woodcut by Escher. This is the circle limit for heaven and hell. It's a finite disk, but it represents an infinite space, and infinity is at the boundary rho equals 1. And as you can see, the metric here at rho equals 1 blows up. That means the distances become infinitely large at the outer boundary. This goes back to actually Penrose's construction. The Penrose diagrams, they represent the infinity of space-time. You see, we recognize that with the null cone, it's not just infinity in spatial directions or infinity in time-like directions. We have also infinity in null directions. And the topology of that infinity is like a cylinder. You see the disks. The disks are like Poincaré cuts, hyperbolic metrics along the cuts. And then in the time direction, you have the regular time direction. But the cylinder is a special kind of cylinder that in applied mathematics is usually unknown. Applied mathematics treats t time still in Newtonian fashion. But what I'm arguing here is that it should be treated in a Minkowskian fashion, in a space-time. So I'm just going to go through. So this was the geometry part. The applied math part is just applying this idea to a wave propagation problem. And for simplicity, I'm taking here the Helmholtz equation. Here you see the unknown, the second radial derivative of the unknown plus some wave number equals 0. It's the standard Helmholtz equation on a domain, again, on an unbounded domain that goes to infinity. The Helmholtz equation doesn't have unique solutions. You have to impose the Sommerfeld radiation condition to ensure uniqueness. And then when you here do this compactification, just map R to some rho, which is finite, you see that the equation is singular. In particular, the wave number becomes infinite towards the boundary. That means you get infinitely many oscillations. So that's the original compactification problem. And then you cannot compactify. You just relabeled your points. You cannot add the point of infinity because it's singular. But if you do the hyperboloidal compactification, I'm not going to go through the derivation of this, but it just becomes a rescaling with a singular factor that comes from this lifting up of the time slices. And the farther you go, the more you lift them up. Essentially at infinity, you lift them up at an infinite value. So a singular transformation leads to a regular equation. It's just degenerate at the principal part. And then when you evaluate it at infinity, you see something like a Sommerfeld radiation condition pop up. So that's an important difference. You do not impose the condition. It just comes out. You know, that has to do with the arrow of time, actually. It's a very interesting aspect of this, but I'm not going to go through that now. I just wanted to demonstrate, because, you know, I'm sure nobody's following the derivation here, just demonstrate this on a simple example, and that's the example of a plane wave in frequency domain. So what you see here is a plane wave, many oscillations on a domain from 0 to 5. Imagine on an infinite domain, of course, you have infinitely many oscillations. And if you map them now from R to rho to a finite domain, you still have infinitely many oscillations. So you haven't solved the problem. You just translated an infinite domain problem to an infinite resolution problem near the boundary, because you cannot even resolve these infinitely many oscillations to plot, let alone to calculate numerically. So what you get is some sort of a singular function as a solution at the outer boundary. But the hyperboloidal rescaling, the compactification with the hyperboloidal time transformation leads to this rescaling, which removes the singular part. And then you have a smooth function. A smooth function that doesn't oscillate much, that you can resolve easily with your numerical methods. And you don't have an outer boundary anymore, because the outer boundary actually is at infinity. And you don't have to, if you look at the equation, because the principal part is degenerate, there are no boundary conditions to be applied, and you have your whole domain solution on your numerical grid. So just to conclude, this leads to a local and exact method. Local because it's local in rho, even though it's infinite in R. And it's exact because there are no reflections from the outer boundary, because actually the outer boundary is at infinity. The method is geometric method. Again, this comes back to the geometry idea. So it's not dependent on any discretization. In your code becomes simpler because you don't have boundary conditions, you don't have boundary data. And all of these advantages, in addition to that, you get the unbounded domain solution. So if you're interested in echo area, in acoustics, radar cross-section, in electromagnetism, or gravitational waveforms, gravitational flux, in general relativity, all of those things are defined mathematically at infinity, and you get that directly. You can also adapt this to high-frequency wave propagation. You see here, this transformation can be modified such that there are less waves on the domain, which means your numerical code will be more efficient, because typically your efficiency is measured by, you need a certain number of points to resolve each wave. So if you have fewer waves, it's much easier to have a numerically accurate computation. And it also handles non-compact sources. Actually next week we'll have a paper about this, nonlinear forcing, variable coefficients. So it's very general. The two disadvantages, you could say, is not as simple as the Helmholtz equation. I don't consider this as much of a disadvantage. If you have seen any of the boundary treatments, they are fairly complicated. So you get rid of the boundary treatment, but your equation looks a little bit longer. I think that's okay. The main restriction is that it only works with smooth boundaries. So far, there might be a way to do it with Cartesian coordinates, but currently we cannot handle corners with this method. That goes back to the fact that the topology of null infinity, again, is a cylinder, as shown in that Penrose diagram from 1965. Anyway, so that's it. Thank you very much. And that's the end of my talk.
Thank you very much, Professor Anil. We are very glad to see your presentation now. Let me ask, is there any question or comments for our presenter? You can ask your question from the Q&A window by writing your question.
My dream is that this method is applied to some real-world problems. It's applied in gravitational waves and black hole calculations. But if any of you has some wave equation problems with boundaries, I will be interested to look into it.
I think there is no question. Let me say something. Actually, I'm working about the just a little bit partial differential equation and the applied mathematics area. I'm very happy to take a chance to see your presentation. It was very interesting and well-designed presentation. I would like to thank you again. And also, I want to thank you one more time for your participation because of the some time difference conditions. I think now you are 4 a.m. According to your local time.
Right.
So we are very happy to see you here. I kindly recommend all the participants who are listening now or listening asynchronously after this webinar, please contact with the Anil Hocam for your questions, and you can reach his studies from the internet. So thank you
for
again.
having me. I appreciate it. Thanks.
Thank you very much. Okay.
Bye-bye.